Hey guys, today we'll see next topic, that is push down automata. What is a push down automata? Why to study this? The first question arises in your mind, that why to study this push down automata. In the previous chapter, we have seen that for a certain languages, the particular languages are not regular. What is a not regular language? For that particular language, it's not possible to construct a finite state machine. Each and every problem has a solution. So we need to think whether there is any other machine which can find a solution for the given problem. The languages which are not regular, for that it is not possible to construct a finite state machine. So for that purpose, we are thinking a next machine. That next machine is a push down automata, whether this machine gives a solution for a given problem. Assume that, say for example, we'll see, is it possible to construct a finite state machine for this language? L is equal to a to the power of n, b to the power of n. Whether is it possible to construct a finite state machine for this language? No. Why? Because here we don't have anything in a finite state machine to count or keep the information for the future reference. So in pushdown automata, we have that facility, that is we have a stack where we are going to store the certain inputs based on the given problem. We'll store the certain inputs, we'll push or pop the inputs from a stack. So that is the reason for certain languages which are not regular, for that language, we'll try to construct a pushdown automata. That is again one other type of machine, that is pushdown automata machine. First we'll define it. How to define this pushdown automata? That is M is equal to pushdown automata is defined as a 6 tuples. M is equal to Q, sigma, tau, delta, Q naught, F. What does the Q stands for? Q stands for a finite set of states. Sigma, input alphabets. Tau is a set of stack alphabets. As I said, compared to our finite state machine, there is one additional name. If you see the block diagram of finite state machine also, there is another one more component, that is stack is present. So here sigma tau represents a set of stack alphabets. Then delta is a transition function. Here the transition function is of the form Q by sigma union epsilon by tau star. Whatever the input alphabets are there, based on that we are going to write the transitions here, add to the Q by tau to the power of star. We'll see one by one. Next, Q naught is a start state and F is a set of final state. So the pushdown automata consists of a 6 tuples. Which are those 6 tuples? Q, sigma, tau, delta, Q naught, F. Q is a finite set of states, sigma input alphabets, tau set of stack alphabets, delta transition function, which is of the mapping of the form Q by sigma union epsilon by tau star to Q by tau star. Q naught is a start state and F is a final state. Next, we'll try to construct what are the actions performed by the PDA. The actions performed by the PDA depends on the current state, the next input symbol, the symbol on top of the stack. So what are the actions performed by the PDA? The actions performed by the PDA are depends on three things, that is current state, input symbol, and the symbol on top of the stacks. The actions performed by the machine consist of changing the state from one state to another state, then replacing the symbol on the stack. So the actions performed by PDA are current state, input symbol, and symbol on top of the stack. The actions performed by machine consist of changing the states from one state to another state and replacing the symbol on the stack. The transition function has the following form. That is, say for example, when we write a transition function in our finite state machine, we used to write it as delta. How we used to write? Delta Q naught comma A is equal to which state it is going. Assume that if it is going to Q1, we used to write it as Q1 A. Means where to which state you are moving, we used to Q naught on A is equal to Q1. Means there is a transition from Q naught to Q1 on input A. But when it comes to a PDA, we are going to write in this fashion, that is delta. You are going to write delta. You are in the state P, input is A, and top of the stack is Z. What we are telling that? Change the state to Q1 here, next state, and stack symbol. So you are in the state P, input is A, top of the stack is Z, is equal to Q comma AZ, means which says that change the state to Q, push this A onto the stack. We are pushing A onto the stack. So here the transition function has the following form: state, input symbol, and stack symbol here. State, input symbol, stack symbol is equal to next state to which state, whether it has should be in the same state or it should go to the another state, next state, comma, stack. Whatever we are going to move into the stack, that stack symbol will be there here. This is how the transitions is performed in our PDA. The next, the as just now I specified that one, then we need to show the instantaneous description of a PDA, whether that particular input string is accepted or rejected. What is this instantaneous description? The current configuration of a PDA at any given instant of time is called as an instantaneous description. In short, we write it as an ID. What does the IDA gives? IDA gives the current state of the PDA, the remaining string to be processed, and the entire content of the stack. Thus, an instantaneous description has a three tuples: current state, string, and the stack contents, where Q is the current state, W is the string to be processed, and A is the current content of the stack, where leftmost symbol in the string alpha is on top of the stack, and rightmost symbol in the alpha is at the bottom of the stack. So whatever we are going to write, so here instantaneous description consists of three tuples: Q, W, and alpha. Next, first we'll try to construct a PDA. Obtain a PDA to accept the language L is equal to A to the power of n, B to the power of n, such that n is greater than or equal to 0. As I said just now, I was discussing that for this it is not possible to construct a finite state machine. Why? Because we don't know the value of n. Finite state machine means there are n number of states. It has to be defined because we don't have anything to store the input or to refer the input later in the steps. So keeping that in mind, we had a next machine. Next machine is our PDA, where we have a stack to store the inputs, to push and pop the inputs into the stack. How do we start with? So as we have taken here A to the power of n, B to the power of n, which indicates that there are equal number of A's and B's, and A should be followed by B. So how do we start with? Initially, you are going to be in the state Q0. So we'll be in the state delta. Will be in the state delta Q0. You are in the state Q0, right? Next, input A. Initially, because A to the power of n, B to the power of n is there, assume that if you are taking input as A, B, it should check for the equal number of A's and B's. Q0, your initially input is A. We don't have anything, the stack is empty. Initial, nothing is there. So I'll write here stack. Initially it is empty. We don't have anything in the stack. So the first transition, you have the input A, nothing is in the stack. What we'll do, we'll push the A onto the stack. That is, we'll write it as P in the state Q0 itself. Let A be pushed onto the stack. Q0 A. A is pushed into the stack. So initially you are in the state Q0, input is A, stack is empty epsilon. We are telling that let you be in the same state Q0, push the A into the stack. Next, what is there? A is there. So you are in which state? You are in the state Q0. So you write it as delta. You are in the state Q0. Next, what is the input? Input is A. Top of the stack is what is there in the stack? The top of the stack is also A. What we need to do, again you have to push this also into the stack. You be in the same state Q0, push this A onto the stack. You can write only one top, or top two contents of the stack can be written. Check here. Now you are in the state Q0, input is A, and top of the stack is A, push the A onto the stack. We have pushed the A onto the stack, A has gone here. Next, assume that if there are 3 A's are there. 3 A's and 3 B's are there. What we'll do now? You are in the state Q naught. Input is A. Top of the stack is A. Already this transition is defined. So whatever the number of A's are there, it will go on pushing using this transition. It will go on push the elements onto the stack. It will push A, 3 A's are there, it will push onto the stack. So what it does, once the B is found, it start popping the elements. See here, one A, one B is found, another A, another B is found, another A, another B will be there. So what we are going to do, until A is found, push the A's into the stack. As soon as B is found, start popping the element from the stack. How do we write the transition? That is delta. You are in the state Q naught itself. You are in the state Q naught itself. Input is B. Top of the stack is A because A is here. So how do we process here? You are in the state Q naught. Input is B. Top of the stack is A. What we have to do? So means for one B, one A has been found into the stack. So pop the element. This B and this A goes. So we are going to write. See, until we push B in the same state. When continuous push or continuous pop is there, then only we need to change the state. Otherwise, no need to change the state. Here, you are in the state Q naught. Input is B. Top of the stack is A. For one B, one A is found. For that purpose, what we are telling? We are telling to pop the element from the stack. So Q1, A change the state. Pushing is finished. Now change the state to Q1. It has been popped. Now you are in which state? You are in the state Q1. What is the input here? Input is B. What is there on the top of the stack? A is there. So write the transition delta Q1 on B, Q1 input because we have changed the state here, delta Q1 on B, Q1 input is B, top of the stack is A, again pop the element. Pop the element from the input symbol from the stack. You are in the state Q1, input is B, top of the stack is A, pop the input from the stack. So again you have pop the input from the stack. Now, until whatever the number of A's are there, whatever the number of B's are there, you will start popping the elements from the stack. At the end, if no more inputs are left out here, if here it is epsilon and stack content is also empty, here no more input string is there, stack content is also empty, then we say that there are equal number of A's and B's. So if you are in the state Q1, input is also empty and stack content is also empty, we say that the string is accepted, else we say that the string is rejected. Assume, say for example, I'll take this example. We'll try to solve this example here. 1 second. So we'll take one example here. Which example we'll take? Okay, fine. I'll consider one example. Assume that we have input as A, 2 A's, 2 B's. What we do? 2 A's will be pushed into the stack. Take the stack. A is pushed into the stack. One more A is pushed into the stack. So these two gone. Then for 2 A's, 1 B, here top of the stack is also A, pop it. This also there, this also there, pop it. So here this is also empty and here is also empty. We say that there are equal number of A's and B's. Assume that if there are extra A's, how it works, if there are extra A's, assume that there are 3 A's. 3 A's and 2 B's. Whether this string should be accepted or rejected. It should be rejected because the number of A's are more than the number of B's. So what it does, 3 A's, it goes here. Both should be empty if the system, if the string has to be accepted because it is equal number of A's and B's. 2 A's, 3 A's. All 3 A's are pushed into the stack. Now 1 B, 1 A, 1 B, 1 A. Here it is epsilon, but here 1 A is left out, which shows that number of A's are more than number of B's. That transition is not defined. Similarly, if assume that if the number of B's are more, B, what it does, A, push this into the stack. Here, B is found, pop this one. Still here B is left out, here this is empty. That transition is also not defined. Why this happens? Because the question is for equal number of A's and B's. As soon as the more number of A's are found, the stack A's will be left out. As soon as the more number of B's are found, input string B's will be left out. So here, according to this, we have defined the transition. Now, formally, how we have defined the PDA? PDA, we have defined M is equal to Q sigma tau delta Q naught F. Which all states we have? Q naught, Q1, Q2 are the states. If you go previously and check, we have the states Q naught, check here, Q naught, Q1 and Q2 are the states. Q naught, Q1, Q2 are the states and input alphabets A and B. What I am pushing into the stack? Only A has been pushed into the stack. So we write tau is equal to A and delta is defined as we what all transitions we have written. Q naught, initially you are in the state Q naught, input is A, top of the stack is empty. So we are going to push the element into the stack. Now we are in the state Q naught, input is A, if top of the stack is also A, then push the element into the stack. So if your input is B and top of the stack is A, pop the element and you have to change the state. Once you change the state, again you need to write the transitions. So Q1 B comma A is equal to again pop the element from the stack. Once the stack content input string is also empty and stack content is also empty, stack is also empty, we say that the string is accepted by the machine. So again, for pushing you are in the state Q0, for popping you are in the state Q1, and while accepting the input string you are going to change the state to Q2. Q2 is the another state. Q0 is the start state and Q0 and Q2 are the final state. Why Q0 and Q2 are the final states? Is why Q0 and Q2 are final states? Why Q0 and Q2 are final states is because without A to the power of n, B to the power of n, n greater than or equal to 0 is there. Means for 0 also, both A is also 0, B is also 0. So Q0 also is going to be the acceptance state. Q2 when there are equal number of A's and B's are there. If n is greater than or equal to 1, if that is the condition, in that case Q0 is not going to be a final state for a given problem. See, we need to construct we can represent the PDA using a transition diagram, transition table. So we'll try to construct the transition diagram. Here, how many states were there? Q0, Q1, Q2 are the states. Q0, Q1. So how we are writing here? Q0 on A, Q0 on A. Okay, when stack content is absolute, we say that B in the state Q0. Let A move this into the stack. We have to write here in this fashion. Q0 to Q0 only it is A, comma, whatever is the stack content, you need to write the stack content and what is moved on to the stack slash A we has to be written. Second one, Q0 A is there, going to the state Q0 itself. So we'll write it as A, comma, A slash A stack content. Then next, from Q0 on B it is going to Q1. Q0 B it is going to Q1. So what we are going to write here? B, comma, A slash epsilon. Similarly, Q1 on B, Q1 on B it is going to Q1 itself. Q1 B, comma, A slash epsilon. Q1 epsilon epsilon go to the Q2 state. That is Q1 epsilon, comma, epsilon slash epsilon go to the Q2 state. Final states are Q0 and Q2 are the final states here. Next, to accept this, we'll check the instantaneous. We'll give the instantaneous moved by the PDA. To accept the string, the sequence of moves made by the PDA for the string A, B, B, B is as follows. Initial ID is you are in the state Q0. Input is A, B, 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 comma, epsilon. The input string we have taken is this is the input string. So here, what we have written first transition is if you are in the state delta, if you are in the state Q0, input is A and top of the stack is epsilon. What we said, push this onto the stack. That is, we have written the transition B in the state Q0 itself, push A onto the stack. This is the first transition what we have defined. So you are in the state Q0, input is A, top of the stack is epsilon. What we are telling, push this A into the stack. So A has been pushed. If you check here, A has been pushed from here to here. The next step, you are in the state Q naught. Input is A and top of the stack is also A. What we need to do, we are defined Q naught, input is A, top of the stack is A. What we need to do, again we need to push this into the stack. That is, you will get it as Q naught AA. Push this also onto the stack. So this A is also pushed onto the stack. Next step, 2A's has been pushed into the stack. Again, you are in the state Q naught. You are in the state, it is Q1. You are in the state Q1, input is A, top of the stack is A. If you are in the state Q1, sorry, it is Q0 only. It is Q0 only. So pushing will do in the state Q0 itself. So you are in the state delta, you are in the state Q0 itself. Input is A, top of the input, you are in the state Q0, input is A, top of the stack is A. What we need to do, if you are in the state Q0, input is A and top of the stack is A, we are defined here. We need to push that into the stack. So Q0 A, push this into the stack. It has been pushed into the stack. Again, you are in the state Q0, input is A, top of the stack is A. Again, push this also into the stack. It has been pushed. Now next, Q0 BB, you are in the state Q0, input is B. We are defined the transition for this. That is delta. You are in the state Q0, input is B, top of the stack is A. What we have said, change the state to Q1 because pushing is finished. Now we are going to pop, change the state to Q1, pop the element, that is B, A has to be popped from the stack, Q1 epsilon. So BA has been pushed. Now you are in which state? You are in the state Q1. You are in the state Q1. So delta in the state Q1, input is B, top of the stack is A. What we are telling? Again, pop the element from the stack. That is B in the state Q1 itself. Pop the element from the stack. Q1 comma epsilon. So we are again popping the element from the stack. Q1 comma epsilon. That is again BA is left out. Next, again same thing. You are in the state Q1. Input is B. Top of the stack is A. Again pop the element from the stack. Now you are in the state Q1. Input is, no more inputs are left out. Here also epsilon. This has been popped. Here this is also epsilon. This is also epsilon. So we say that Q1 we are written the final transition, that is delta. If we are in the state Q1, input is epsilon and top of the stack is also epsilon. Input is epsilon and top of the stack is epsilon. What we are telling? Change the state to Q2. Q2 epsilon. So we say that Q2 epsilon. We say here, next transition here, final configuration, we tell it as Q2 comma epsilon. That is, we are reached to a final state Q2 comma epsilon. So once we reach to a final configuration Q2 final state, we say that the string is accepted by the machine. As this is the final state, we say that this string is accepted by the machine. We'll see one example which has to be rejected here. So here, this is the number of A's are less than number of B's. So initial description as usual, what we have seen just now, Q naught AA B, comma epsilon, Q naught AA, Q naught input is A, top of the stack is epsilon. What we are telling, push that element into the stack, which has been pushed onto the stack. Again, next you are in the state Q naught. Input is A, top of the stack is A, push the element into the stack. Similarly, when you are in the state Q naught B1, we just change the state to Q1 B A, pop the element from the stack. Next step again, Q1 B epsilon. So what we are telling here, the no more contents are there in the stack because 1A is less than number of B's. So we say that this transition is Q1 B epsilon transition is not defined. We say that the string is rejected. This is not defined. So the string is rejected by the PDA. So we are seeing how what it is going to accept and what it is going to reject. The strings which all will, if there are equal number of A's and B's, the string will be accepted. If there are unequal number of A's and B's, then the string will be rejected. If there are more number of A's in the more number of A's in the stack, A's will be left out. If there are number of Bs are more compared to number of As, then in input Bs will be left out.